Hello, I'm not in my usual place today. I'm actually at the University of Oxford because I have a little story for you. As you may know, I did all of my degrees at the University of Manchester. I actually applied to the University of Oxford way back in the day, but I didn't even get an interview because I flubbed the admissions test. But I've always wondered what an Oxford interview is like. Luckily, I found the perfect person to help me with that.
Hello, I am Dr. Tom Crawford. I am a mathematician at the University of Oxford, which is why we're here in this lovely old library at St Edmund Hall, which is the college where I teach. And I also run my own YouTube channel, Tom Rocks Maths, and you possibly may recognize me from some number file videos. So basically, this is how this happened. We are both fellow maths YouTubers, and Alex wants to experience an Oxford interview. So as somebody who does the interviews every year for undergraduate study here at the university, I'm
here to be tortured, like all of your prospective students.
I feel like you already have a slight misconception. I think you're going to love this. We'll see, but I think he is going to love this whole process. And hopefully you will enjoy watching him squirm. No, I'll be nice. The interview itself is actually just part of the admissions process, again, as Alex hinted. So we have the actual application from the students. We also have the admissions test, and then we select a proportion of those students to come down for interview, and this is like the final stage in that admissions process. So I'm very sorry to hear that you didn't get your interview the first time. Clearly mistakes were made, because we all know Alex is clearly a fantastic mathematician.
Sure.
So this is not a foolproof.
We'll see about that.
This is not a foolproof process. However, the problems are, I designed the problems to be fun and enjoyable, and we're going to work through them together to try to get to the solution. So I just want to emphasize for everyone watching and for Alex here, who doesn't really know what to expect at this point, this is going to be maths questions that we're going to be working through, and we're very much doing this as a collaborative effort. I am not trying to put you on the spot or test you or show you up. We're going to work through what are hopefully interesting problems and enjoy the process as much as we can.
As much as we can.
All right, are you... Should we just do it? Are you feeling...
Let's go.
Alex from the future here. I'm going to drop in a few thought bubbles here and there to let you know what I was thinking along the way, but none will spoil the solutions if you want to work alongside me. This video is mostly unedited, even when I'm struggling, because I wanted to give you the problem-solving process in full. And I did struggle, especially when Tom asked me some probability questions which are absolutely not my strength. Luckily, there are some great courses on probability over at brilliant.org, this video's sponsor. No matter your level, Brilliant is a learning platform with courses for you, and you can try it for free today. Despite holding a PhD in pure mathematics, I always struggled with probability because I don't have a strong intuition for that subject, and that's why I love Brilliant's interactive lessons that encourage you to experiment and get a feel for the subject rather than just sleepwalking through the material. There are bite-sized lessons from the very basics of probability and up through more advanced topics like Bayes' theorem. And as you use Brilliant, it customizes your experience so you can learn at your own pace. Maybe you want to build your intuition for other topics, or learn some physics or computer science. Whatever your needs, Brilliant will have courses to suit you. Try Brilliant for a whole month for free today by following my link brilliant.org/anotherroof. The first 200 of you to sign up using my link will get 20% off their annual subscription. That's brilliant.org/anotherroof. Thanks to Brilliant for supporting my channel, and now let's get into these questions.
Okay, so the first question is going to be related to functions, and we're thinking about the following. We're going to have a function, f of x, and this is going to be defined such that f of x plus 2 times f of 1 divided by 1 minus x is going to be equal to x. So it's an implicitly defined function, and I would like you to try and work out what is the value of f of 3. That is all there is to it at this point.
All right. Never regretted anything so quickly in my life. So, yeah, I think the natural thing to start with is just to get a feel for what's going on by substituting in. Obviously, we're going to end up with something horrible here. So 1 over 1 subtract 3, that's minus a half. That equals 3 actually, doesn't it?
Yes.
Okay, so now what is f of minus a half? Could something be done where we substitute minus a half in there? 1 over 1 subtract a half is going to be 2/3. So obviously this is the really awkward thing, isn't it?
Mm-hmm.
So my instinct is kind of like, is there a convenient number that you can put in?
Yeah.
So that.
Well, if you
Okay,
sort of.
yeah, okay. Maybe if we want these arguments to be the same, what number will that yield? I'm kind of looking for clues. So
That's not a terrible idea. No, I think that could be a. Probably. I think it's an equation you should be able to solve.
yeah, I was just trying to see if it's going to come out to be anything nice. I don't think it is. Should we try it?
I would strongly encourage.
Experimentation?
Yes,
Okay.
definitely. You had the right idea initially when you were saying, well, let's just plug in 3 and let's see what happens, and let's plug in minus a
Yeah.
half, let's see what happens. Sort of.
This just looks gross though, doesn't it? So what is that? Obviously it doesn't factorize. So does it even have... Is this a real valued function?
Let's say it's a real valued function.
Yeah. You're not going to trip me up on that.
No.
Obviously, you
I
design
like
these.
your way of thinking, though.
You
Yeah,
design
yeah.
these problems to be like accessible to school kids.
Yes.
So it's like
We
you
would
shouldn't need anything else.
You're right. You shouldn't need anything beyond high school maths, but a lot of the students we are interviewing, we would actually encourage them to take further maths. It's not a requirement, but most of them will have taken further maths and therefore will have seen complex numbers. So I think it would be fair to ask questions based on complex numbers, but that is not what's going on here.
Yeah. So this doesn't have any real solutions, is what I'm getting.
So that's your discriminant then, is that?
Yeah.
B squared minus 4ac.
Yeah.
Yeah.
So that's negative, which is telling me it doesn't have any real roots, which means I don't think there is a value of x that you can substitute in there such that f of x is the same thing as f of 1 over 1 minus x. I wanted that because if these are the same, then we get 3 of something equals something, and then you've got it.
No, it's a
So-
very, very good approach. Very, very good idea. But as you've
But not the right
realized, it's in this particular situation isn't going to work, but I think it's an excellent way to approach the problem.
Yeah.
But you did mention something a little bit earlier, which I think
Sticking minus a half in there, and then
feels like the next sort of
that's what I was thinking.
thing to
Okay,
try.
let's just see if we kind of, bump into ourselves. If we put minus a half in, it's going to produce something else. How do I scroll on this?
you swipe with.
That's not part of the test, is it? Okay, f of negative a half plus 2 f of... Let me just make sure I've got that right. 1 subtract minus a half is 3 halves, so it's
Yep.
2/3.
I agree. Yep.
And then,
Is equal to x.
which is negative a half.
Yep.
So now, let's just see if we do 2/3 plus 2 f of... So 1 minus that, and then take the reciprocal. So this is good. So that this looks promising. So f of 3 plus 2, and then I'm going to rearrange that second one to get minus a half subtract 2 f of 2/3. Not going to do too many steps at once because this is
Sensible.
when I
Yep.
screw it up. But obviously we can see what's going to happen here. I can fold this one inside there, pointing as if the audience can see what I'm doing. So this is 2/3 subtract 2 f of 3. And that's what I wanted before,
Yeah.
where we just have f of one thing. Okay, this seems... Sorry.
All right.
I feel like an old man. You can't even like that. I don't think this is a clever way to expand this. let's just behave ourselves and do it properly. How many brackets do you need? That's the worst 3 I've ever drawn. Okay, I really don't want to make a mistake here. So that's why I'm being so... I'd usually be a lot more cavalier with this.
Yeah.
Probably why I flubbed the admissions test. So f of 3, take 1, take 8/3, plus 8 f of 3 is equal to 3.
Yeah.
Okay, and then we bang everything over there. So f of 3 is equal to, that's going to be 4 plus 8/3, and then we could divide by 9.
Mm-hmm.
Yeah?
I think so, yeah.
You want it in a nice form, I presume?
Well, I know what the answer is, and it's not...
I'm
in my head, it's not.
I'm a pure mathematician, you know, a solution exists.
Yeah.
So...
Let's put it on a common denominator.
Let's sort it out. Yeah, okay. So this is 4/9 plus 8/27, which another word for 4/9 is going to be 12. So 20 over 27?
Exactly, yeah. F of 3, 20 over 27.
All right, okay. Not too bad. I think I had a, like you say, I think I had a good idea that didn't go anywhere.
Yeah.
So it was a bad idea.
No.
Good in theory, but for the question at hand, probably just needed to go with my first instinct and just keep trying things. My feeling was actually that because it was a 1 over something, I just thought that was going to be like an infinite descent into...
Which it could well have been, and then your other method might have been the way to do it, right?
Yeah.
I think you sort of, you chose what to me feel like the 2 routes to a solution, right? Is like you spotted, it's almost like just this one in a way is possibly like a slightly simpler method of trying to solve it, which is maybe why you were worried it wasn't going to work.
Too
because
easy.
it was just
Too
continuing substitution. But you would be surprised at... I think it's just because you are obviously a trained mathematician now, so...
Maybe. not that this area of maths is my my
But you
usual...
know how to think like a mathematician, and that's what we're trying to do
Yeah.
in these interview questions.
I suppose so.
So that's why your first idea, it didn't work, but I'm very keen to stress it wasn't a bad idea.
Okay.
It was a good idea, and if I'm seeing that from a student in this setting, I'm impressed.
I see.
That to me is a very insightful thought into the question. So I'd almost...
So nice, isn't he?
I'd almost argue that you did better by mentioning that.
Okay.
And then figuring out that didn't work, so let's do it this way.
No, I agree. Like, from my experience teaching, you know, I want to see them just, like, you know, getting their hands dirty, get stuck in with a problem. It doesn't matter if it doesn't go anywhere because, yeah, that technique might have been applicable in a different problem.
Yeah.
All right, good.
Okay, so that was part 1.
Part
that was
1.
the first one.
Okay. Not over yet. So I'm not in Oxford University yet. You have to do more than just solve one problem.
Yeah, so that one's sort of like part 1
Okay.
of a question, and I've got a second question which is completely unrelated, but that's mainly, you know, I could possibly, if using this, lead into a further exploration of functions. There's obviously interesting questions you can ask about range and domain and possibly sketching things. Who knows?
Let's not do any of that. Let's
But
yeah.
no, I want to kind of switch focus and give you a chance to just sort of think about a completely different area of maths and sort of, and again, this is something that you could be expected in an admissions interview, sort of like, it's not necessarily that we're like ticking boxes as in student can do this, because that's been tested in all your exams. You've done an admissions test, you've done A-levels or school qualifications. So we know you're good at doing a whole range of topics.
Yeah.
But just in terms of like different ways of thinking, we might just sort of, you know, switch focus. So
This whole time I'm just thinking, all right, what are you setting me up for here then? Okay.
So, this one is going to be in probability. You can see him shaking his head. It's going to be in probability, and we're going to think about the zeta function, which you probably never thought about in a probability concept before.
Don't think I've ever
I
thought
don't
about
know.
the zeta function before. to be honest.
Okay, well, so the zeta function is the Riemann zeta function.
Yeah.
So zeta of s, you input s, and it's the sum from n equals 1 to infinity of 1 divided by n to the power s. And now for the full zeta function, s can be complex, but
Yeah.
we're going to keep things simple.
Okay.
So we're going to say that s is a positive, s is a strictly greater than 1 real number. So first of all, we can see that it definitely converges. because if it was S was 1, it of course would diverge harmonic series. Because S is bigger than 1, I am giving you this fact. We definitely know it converges, so you don't have to worry.
That's generous of you, thank you.
You may have already known it, but just to be, again,
Just to be sure, yeah.
It's helpful, it's helpful in these settings to clarify what I am allowing you to assume.
Yeah, definitely,
right?
yeah.
So you don't have to worry about convergence. And now we're going to define a probability mass function. So we're going to say that the random variable x.
You're not going to ask me to solve the Riemann hypothesis, are you?
That would be good.
Yeah, get one of your prospective students to do it.
Yeah, claim part of the prize money. So we're going to have random variable x, and we're going to define this by the probability mass function, which says the probability that x is equal to an integer n is going to be defined by 1 divided by n to the power s, multiplied by 1 divided by the zeta function at the point s, and n is greater than or equal to 1 and is an integer. So just like any probability function, random variable x, it takes values 1, 2, 3, 4, 5, blah, 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 blah. And it's discrete. I think you were telling me earlier you prefer discrete to continuous objects, so maybe not in this setting. But
absolutely not.
This is...
It's making me feel worse and worse.
Okay, now, the first thing is we want to check that this is a well-defined probability mass function.
Yes.
So if I'm talking about probability, and there's not really a right or wrong answer here, but what kind of things should we be thinking about?
It's got to be between 0 and 1.
Perfect. It has to be between 0 and 1, so we would expect these values to be between 0 and 1. And what about the total?
Sum to 1.
They have to sum to 1. So can you sort of check that for me? So given this definition, how would you check that the probability of x being 1 plus the probability of it being 2, 3, all the way up to infinity does indeed total 1? Because that's what we need.
Yes.
For this to be well defined.
Okay.
Because we're going to do some probability-based stuff, but it doesn't make sense to do that if it's not a well-defined random variable in the first place.
Yep. Okay.
So that's the first part.
So we just need to do the probability that x equals, so n is 1 or greater, so that means we just need to add up all of the probabilities x is equal to n from n equals 1 up to infinity, I guess.
Yes.
And that is the sum from n equals 1 to infinity of 1 over n to the s times 1 over zeta of s. And now zeta of s is just that. So this is strange because 1 over that Oh, yeah, okay. Yeah, I don't know why I was getting... I thought something else was going to be happening there. So that's n equals 1 to infinity. And then, yeah, that is just that on itself. So it's 1.
Yeah.
Which is what I thought was going to happen. I went in there all gusto.
Yeah.
And then I got to that and I'm like, hang on a minute. It's not that easy, but it is.
Yeah.
Okay, so, yeah, fairly confident that the probability is sum to 1. Worryingly straightforward. What else have you got in store for me here?
So we are working with the same function, same probability mass function.
Of course.
And now we're going to suppose the following. So k is going to be an integer greater than or equal to 2. And I'd like to know what is the probability that our random variable x is divisible by k. And again, just to remind you, we said, what did we say? We said the probability that x is equal to an integer value, n is 1 over n to the power s times 1 over the zeta function of s, didn't we? Okay, so for any given, if I give you an integer, 2 or greater, I'd like you to tell me what is the probability that our random variable is divisible by that number.
Okay, so I'm just going to write the zeta function up here again. So, okay, x is divisible by k. So it's some multiple of k. So that means we want the probability that x is equal to k, or it's equal to 2k, or 3k, or and so on.
Yes.
Right? So let's do that. So it's going to be one of these sums again, isn't it? So that's going to be the sum. I'm just thinking about the variable that I want to use here. So the sum of x is equal to I k for I equals 1 to infinity. I don't know if I need to do that, but I'm just, because we've already got an n up there.
Yep.
I don't want to
No problem. Yep.
get awkward. So, yeah. That's the sum of I equals 1 to infinity of 1 over I to the s ik to the s times 1 over zeta of s.
Yep.
This is, so we've got, do I want to do that? So we're basically doing n equals ik. Do I want to do, let's do, sorry, is it that one?
On the left, yeah.
Let's do I equals 1 to infinity of ik to the power s.
So that is what you've done here, but this is just zeta of s, which is defined like this.
Yeah, that's where I was getting a bit.
So I would argue that this is not zeta of s. When I look at that, I think it's actually easier if you leave that as 1 over zeta s. I don't think you need the second sum.
Okay.
If I could offer a...
Yeah, a nudge. So, yeah, I just thought something else was going to happen when we cancel out those sums. But yeah, okay, let's keep it as zeta of s. Okay.
And something else that, again, this is not always true, but is usually how these questions are structured. The stuff we've done at the beginning is going to be helpful for the parts later on. And that's particularly true in this one.
Yeah, okay, yeah, that's it's often what happens in exams, isn't it? You know,
Yes.
you use the part A and part B.
Exactly.
Because yeah, I was thinking about that. So what I'm thinking is we want to get that k out of there because k has got nothing to do with this.
Yep.
So if we do this, this is basically 1 over k to the power of s.
Yep.
Times the sum. So we get 1 over, so this is now just I equals 1 to infinity
Yep.
of I to the power of s times 1 over zeta of s.
Yep.
And we know that that's 1 because by part A.
Yes.
So the answer is just 1 over k to the s.
Yeah. Which is quite nice.
It is quite nice.
Probability of a randomly chosen number. Well, I say randomly according to this distribution, of course. It's not like a uniform distribution where each number is equally likely.
Yeah,
there is a spread, but a randomly chosen integer.
And it makes sense because if k is larger, there are fewer multiples of that integer
Yeah.
in a manner of speaking.
Yes.
I mean, if a number theorist, I think, would take umbrage with that. But like,
Yeah, no, I agree.
you expect if k is 2, then half of the integers are x could be divisible by 2 more often than it's divisible by 3. So the fact that it's 1 over k, as you make k larger, the probability gets smaller. So I think I'm happy with that.
Yeah.
Well, that's the answer, so I should be happy with it. But,
I'm also happy with that because that is the answer.
Okay.
All right. So that is part 2, and that was the final part.
right.
Okay. So,
He's still
and
torturing
again,
me with
we're
it.
building up, right? We've sort of used the first part to help us with the second part. So the third part, again, using these same ideas, same concepts we've been thinking about. We've now established this random variable x, shown its probability distribution. We've looked at the probability of x being divisible by a number k, 1 over k to the s. Now, if we say that d subscript k is the event that x is divisible by k, because we're going to consider several of these together. Right, so as an example, d2 intersect d3, what would that mean?
The probability that x is divisible by 2 and 3.
Yes,
So,
it's all x that are divisible by 2 and 3.
yeah.
Right, and then we might want the probability of d2 intersect d3.
Yeah, got it.
Okay. So what I would like you to work out is, in fact, going to be what is the probability of the intersection of dp over all primes p.
Yeah, okay, interesting. Because I was just thinking about that 2 and 3 example, basically asking about d6 there, aren't you? Because if it's divisible by 2 and 3, then it's divisible by 6. You know,
What would okay? So let's maybe start with what is, because I think this actually will be constructive. What is the probability of d2 intersect d3?
well, it'll be... I don't just want to say that it's the probability of d2 times the probability of d3, because they're not... They could happen at the same time.
So you're asking. So you're beginning to talk here about independence of events.
Yeah, like...
So if they are independent events, what is the probability of d2 intersect d3?
Then they do just times.
Yeah. So
they
does being divisible by 2 have any impact on being divisible?
Well, no. Yeah, okay. Yeah, I was thinking about the other one, mutual exclusivity, wasn't I? Because
think so.
yeah, because if d6, like if 6, for example, is divisible by 2 and 3. Yeah. Okay. So that's d2 times d3, which will be 1 over... What was it? 1 over k to the s.
Yes.
So that times 1 over 3 to the s.
Yes, the probability of that. Not just
Yeah,
the
P of...
intersection.
Yeah, yeah.
P of that, yes. P of that, I agree, yes. So, again, I'm going to allow you to generalize this independence for an infinite number of primes.
Okay.
That is something that you might worry about and that we might have to establish. But for this purpose, again, I'm going to say, I will give you the information that these are independent events, even for an infinite collection.
Okay. Then it's just all of the dp's times together. Should we use a big pi? So it's the product of all across all p of d of 1 over p to the s.
Mm-hmm. Yeah.
Okay.
Right. Now, what if
Here we go.
we now consider the complement of dp?
Right. So
So we want to work out what is the probability of the intersection of dp complement over all primes.
okay. So if the probability that dp happens is 1 over p to the s.
Yep.
So the probability that dp doesn't happen
Yep.
is 1 minus 1 over p to the s.
I agree.
So if we times all of these together, is it just going to be the big product of 1 minus 1 over p to the s? Yeah.
So, we now have, and this is where the magic's going to happen, by the way.
Well, I'm waiting for some magic.
So
This
this
looks very familiar, actually.
I thought it might. We now have the probability of dp complement, the infinite intersection. It might be worth writing this down, actually, maybe just in like a sort of final equation in a box or something. So you've got this formula, and what's it? That's equal to the probability of the infinite intersection of the complements.
Okay, so probability of a big old intersection across all prime
Yep.
p of dp complement. And dp complement, just get it in my head, that is the event that x is not divisible by p.
Yes.
So if you pick some prime p like 3, then it's got to be a number like 4 or 5 to be, yeah. Okay.
To not be in D3.
Yeah,
Yes,
I just want to iron that out in my head because there's a lot of creases in there.
Going to be very helpful. So I'm glad you did that because that was going to be my next question.
That's why I had the funny thing about independence. But again,
Yeah.
you know, if you pick a number, if it's not divisible by something or other, it shouldn't have any bearing on,
I agree.
yeah. But this is where my intuition is not,
It's serving you well. It's serving you well so far.
yeah.
Now, as I said, this is where the magic happens because
There's got to be some relationship to that thing we had before.
it's going to be related to the zeta function.
Yeah.
Because I want you to think about what does the left-hand side of this expression actually mean?
Yeah.
Like in words, like let's sort of...
Yeah, so, yeah, D2 complement, that's the probability that the event is not, the x is not divisible by 2.
Yes.
So if it's not divisible by 2, it's not divisible by 3, it's not divisible by 5, which basically means it can't happen. Or it means that it's...
So close. It can't be divisible by 2, 3, 5, 7, 11, etc., etc., etc. Can you give me a number that isn't divisible by any prime?
1.
So this event is the probability that...
That x is equal to 1. Yeah.
Right, and what's the... We have a formula for that.
We do.
Not?
The probability that x is equal to 1. So that was...
Probability that x is equal to n was 1 over n to the s times 1 over zeta s.
Times 1 over zeta of
S.
s.
Well, what's 1 to the s? Where s is a positive integer.
1.
So it's just 1 over zeta s.
Yeah. So, yeah, okay, so yeah, 1 over
So you
zeta of s.
can... So if you erase this now and replace it with 1 over zeta s.
And this is going to give us an alternate formula for the zeta function.
It's exactly what it's going to give us.
Yeah.
So that now tells us that this form you've got written here is 1 over zeta s.
And if we spin it round,
If you
then we
spin it
get
round,
that zeta of s is 1 over big product of all of that.
which is actually Euler's formula for the zeta
The Euler,
function.
yeah, because this is an Euler product, isn't it?
Yeah.
Where it's a product across primes. Because people often ask, what is the relationship between the zeta function and the primes? Because you've got this whole zeta thing
Yeah.
that is some kind of weird infinite series. It's got nothing to do with primes, except there's this relationship here. And then obviously smarter people than me know why it's even more closely tied with primes and things
Yeah.
like that. So that's a great question. Because it's doable, but it's also, you get a satisfying reward out of it.
I find it so satisfying.
Yeah.
You know, people watching probably saw me smiling as you were beginning to figure out that we'd done the
Yeah.
reformulation of zeta. Because you don't expect it because it's set in probability. It's,
Yeah.
So it's one of my favourite questions I've ever come across. My colleague came up with this. I can't claim this was me.
Thanks. I'm gonna steal this one.
So overall, how was your interview experience?
Yeah, pretty good actually. You have a very warm demeanour that puts
Thank
people at ease, which is very nice.
Yeah.
I think that's what you're all about, really. You know, I think there's a stereotype, I think, about Oxford and about Oxford academics. And I've often, because I've done a lot of outreach work, you try to dispel what a academic looks
Yeah.
like. And you know, they walk in and they see a guy who's, you know, full of tattoos, and you know, it's like, oh, actually, seems like a pretty normal guy. So like, obviously, you put me at ease. it was nice to work through the problems together. I felt like you gave me just enough hints that I wasn't getting frustrated with where it was going, but just a little nudge here and there, just so that we could kind of get to the point of the question.
I think of it as you're walking along a path, and every now and then you stray a little bit, and if you stray too far, I just kind of nudge you back towards the path.
Yeah,
I'm not picking you up and putting you on the path.
Yeah.
But you're walking off, and I'm like, well, maybe just kind of go back that way a little bit.
Yeah. No, it's it was pleasant.
Good.
Yeah. Don't know what I was so worried about.
Do you feel happy that you have now been able to experience?
I think so. Yeah. Yeah, it's always been a weird feeling because I don't know, when you're doing your A levels, you feel like you're on fire, you feel like nothing can stop you, and then that was a bit of a brick wall in my face where I was like, oh, geez, I really, yeah. But I think you actually need that sometimes, don't you? To actually, I should have prepared more for that admissions test, and I should have. It's not something that I've always really regretted, but it's always been in the back of my mind as like, what is this interview actually like? What is it like to actually sit down with, an Oxford person and tackle some questions together? So thank you for that.
You're welcome. No, it's my pleasure to share this with you and share it with everybody watching.
Absolutely.
We hope you have enjoyed this. Obviously, you're on Alex's channel, so you should be subscribed to his channel by now. But also, if you haven't seen any of my stuff, do head over to Tom Rocks Maths. Alex is thankfully nodding as I'm telling you all to do something.
Absolutely, because I thought it would be interesting because you've obviously given a lot of these questions to a lot of very scared students. What would it be like for someone to ask Tom some questions? So if you want to check that out, head on over to Tom's channel where I take a little bit of revenge